All right, continuing on with week 4. Here's another example out of Thompson. I debated whether to even cover this. Sort of a, I don't know. I'm not sure it makes a lot of sense to for our purposes, but it is sort of a. It's in the book. Why not? So we show. I always hate these problems that say show. I don't know what to do. Show. Am I showing? Maybe I'll show. What basically we're saying is that if you have this thing going on, let's see, I tried to make a bunch of them, but I didn't. That if you compare that one to this one to this one, and I didn't draw this line very well. Let me see if I don't redraw this line. Didn't do a very good job of that either. There you go. All right, so if right here is one period, here's another period, here's another period. Now we're going to say we're going to compare this one, XO, right? This is the value of X right here, to this one over here, which is 3 over, right? So we could call it X3, or we could just say that it's a lot, XN. It's a whole bunch of the things. And so if you just take that ratio of this one to this one and take the log, and then, but then also divide it by how many periods have we gone on to right there. I guess maybe I should have drawn that one, like that right there, right in between there and there, and then another one in between here and here, right? And they should actually be equal to each other. That's what we want to show, right? So basically, you could say that, and I don't like the way that the book wrote this, so I guess that's one of my reasons for putting in there. We could say that here's the assumption that all of these are going to be the same. And by the way, I have actually hit something that had damping in it and counted and recorded the response, filtering it out so that we could actually get the some of the log in there. But by the way, the filtering of data will affect the data a lot, so you have to be really careful there. And this did not hold true. But it's sort of like, this is sort of like linear damping, and the world's not linear. So we have kind of like xn minus 1 over xn. That's the basic idea. So if we go ahead and say, what is x to xn? We go, well, that's xo to x1 times x1 to x2 times x2 divided by x3, and you go dot 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 dot, and eventually we will get to the xn minus 1 over xn, right? So we can see that they all cancel out with each other, right? And presumably to the last one. And so that's the same thing if you replace the main equation here, where we have ln is x, let's call it n over, that's bad, let's use the same term right here, x, whatever number you have, n minus 1 to xn, right? Which is the same thing as saying xn over xn plus 1. It's just depending what you consider n to be. That's the same thing as going, well, they're all the same as we've set up here. So we have this times this times this, which is essentially the same thing, blah, 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 on and on. I keep messing it up, sorry, e to that. So we've just multiplied all these by each other until they all equal e to the n del, right? So if we have that x naught over xn, it's equal to e to the n del. Well, if you take the natural log of that, you end up getting n del, right? And therefore, del is equal to 1 over n natural log of x over xn. And I encourage you to read Thompson's solution to this right here. I think he kind of messes up. I think it might even be a mistake in the book in the way that he writes this out, because I'm very certain of what I've just done is correct, but the way he writes it is a little confusing, ambiguous, and I think actually kind of wrong. So I've included here the number, this n right here, from this. This might be an interesting thing. It's the number of cycles until we get 50% reduction in the amplitude. Something you should note is that this E kind of goes on forever, right? So if E by itself, and it never quite reaches, of course, that doesn't match reality. We know that the thing will eventually stop. Yeah, so instead, let's just have an arbitrary thing to, consider and look at. It's like how many cycles, of this thing, going wee back and forth does it take? How many n's does it take until this thing is reduced from its original amplitude, which is something like that right there, down to right here? Well, we can, yeah, it's a good measure, I guess, right here. So you can kind of see that as the damping goes down below, damping effect goes down below here, it takes a whole lot just to reduce it down to 50%. But you could use a graph like this when you're trying to do some kind of design, and you have some desired thing, like it takes one cycle to get to 50%. You could design with the damping factor if that was like your design goal. I think I'll go to another video for the next. Do I have another example? Yes, I do. Well, I have a lot of examples in this one. Is that too many examples? Can you have too many examples? Can you be too rich? I don't know. Probably.